Session we are going to discuss about Amba protocols and what are all the Amba protocols, why it is needed. Okay. Then we are going to see about APP protocol. So Amba stands for Advanced Microcontroller Bus Architecture. Okay. So Amba it defines some set of protocols specifications. Okay. Why it is needed means okay, if you take a SOC, it consists of multiple functional blocks. IPs, different IPs are there, and microprocessor and microcontrollers. Everything is available inside a single SOC. Okay. So how the data is transferred between the IPs, okay, between the functional block and the processor or a controller. Okay. Then how it is communicated with the external peripherals. So everything happened in a proper way, right? So that is defined by a protocol. Okay. So ARM, if you know ARM, they are defining some Amba protocols. Okay. They are defining some set of standards. Okay. Based on that, all the signals are properly communicate between the processor or functional blocks. Okay, a design that is inside SOC, typically we have one or more controllers, processors, okay, and we have several components like memory, external memory, bridge, digital signal process, DMA unit, okay, accelerator, and various peripherals. In the boundaries, you have USB, UART, PCIe, and I2C, those things. So all are integrated with a single chip. So to make the communication proper, we need to define a set of standards. Okay, that's a protocol that is defined by Amba. So the primary motivation of Amba protocol is to have a standard and efficient way to interconnect these blocks and with the reuse across multiple designs. Okay, that's why we need this Amba protocols. Let's see what are all the protocols we are using and where we are using. So this is a SOC structure, simple SOC structure. Okay, inside here we have a high performance ARM processor. We have a DMA bus master and high bandwidth on chip RAM. Then this is the external memory interface. This is a high bandwidth, and the boundaries we have a UART, okay, keypad, input output, and timer. So these connections, the interface is connecting the process with DMA. Okay, so it connects the high external memory interface to the DMA. So everything is communication happens with the protocol. Here we are using AHB or a ASB protocol. Okay, AHB stands for Advanced High Performance Bus, and ASB stands for Advanced System Bus. Okay, so these protocols are high-speed protocols. So we can transfer multiple bits at the same time. So the bandwidth is very high compared to APP protocol. So for speed, faster communication and more throughput, data transfer happens to the AHP protocol. That's why we are keeping these AHP protocols inside to communicate with the processor and with the different IPs. It should be happened very fast, right? So APP is a protocol used to it is act between interface between the external peripherals with the processor. Okay. So it is a low bandwidth protocol. The performance will be low. Usually we use this for serial communication. So UART is one of the protocol used for serial communication. So those data you can receive from the external peripheral. Okay. Then these signals will be sent to the processor, okay, through the bridge. Okay, here I use APP protocol. Here I use AHP protocol. So how I can convert this signal into this signal with the help of a bridge? I can able to convert APP into AHP, and I can transfer the data to the processor or anywhere in the IP. Initially, in 1995, Amba released the first version. Okay. So there we have two protocols. One is ASB Advanced System Bus that is used inside the core SoC, and APP is also used inside the core only, but it is used to communicate with the external peripherals. APP. Then later in 1999, Amba 2 they released AHP Advanced High Speed Bus Protocol, and then AHP Lite, ML AHP. Okay. Then ABP2 version was released. Then 2003 Amba 3. Okay. They introduced AXI. AXI stands for Advanced Extensible Interface. So here they introduce point-to-point connectivity, because when the technology improves, more number of functional blocks are embedded into SoC. Okay. So we need a faster communication between the IPs. So some advanced protocols are introduced to achieve that. Then APP version 1 they introduced. Then 2010 ACE, that is AXI coherency extension, with a we integrated the cache memory concept here. Then AXP Lite, AXI4, AXI4 Lite, then AXI Stream. Those protocols are introduced into 2010. Then APP version 2 was released. Now currently we are using in mobile phones inside the chip. Okay, we are using CHI. So coherent hub interface is a very high speed protocol is used inside the SoC. Here AXI, AHB, and APP are internal to the microcontroller. They are connect different peripheral controller to the core. These protocols are used inside the core. The APP is used to receive the serial data, and it is through the which it will convert into AXI, and it will send to the IPs or a controller or processor. Here these protocols I2C, SPI, here I mentioned only two. So you have different protocols here. So these are all serial protocols. Through this the external peripheral is connected. Okay. So through this protocol we can able to receive and we can able to send the data. If you take a laptop, you have external peripherals like USB. Okay, you have a serial ports, everything have, right? So there through, for example, you take a USB, it is one of the serial protocol. Okay, but it is a high speed. Through that we can able to send the data. So it will receive here, and here we have a bridge. So that will convert, okay, that APP or AHB, that will convert into AXF protocol. Okay, that signals get mapped with the AXI signals. Then through this AXI signal interface, it can reach to the processor or a controller or a DMA, those things. These are the few major difference between the protocols. Here I mentioned APP, AHP, and AXI. So about the APP used for connecting low bandwidth peripherals. So it is only applicable for a low bandwidth requirements and don't require for high performance. And AHP is used for connecting components that need higher bandwidth and high performance. Where we need a higher bandwidth and high performance, we have to use AHP protocol. That's why we are using AHP protocol inside the core. Okay. Then AXI used for connecting components that need higher bandwidth and high performance. This is just we are introducing few more additional features AHP, and we have AXI. This is also used for high bandwidth and high performance. And for APP, it is a simple non-pipeline protocol. Okay, here we don't have a pipelining concept. Okay, and it supports pipelining concept. Pipelining concept in the sense for a single cycle it can do multiple processes. For example, right, fetch, okay, decode and execute. Okay, these are the few steps will happen in a processor. So in a single clock cycle, first process fetch is happening. Okay, in the next cycle, first process decode is happening. The second cycle, next process fetch is happening. Okay, so the same clock cycle, different processes are running. So that is the concept of pipeline. Okay. So AHP it will support pipelining concept, and AXI also support pipelining concept. Here in the here for a first master, for example, for AHP, we have two master, okay, and two slaves. So first cycle, first master will access the slave, first slave. Okay, it will send the address phrase. In the second cycle, for the first master, for the first slave, it will send the data. First cycle is address, second cycle is data. In the second cycle, second master can able to send the address phrase for the second slave. So multiple process happen at the same clock. Okay, that is the concept of pipeline. Then here in APP, one master, multiple slaves are connected. So read and write share the same set of signals. Here one master, if we have multiple slaves, like here we can connect up to 15 slaves. So all the, for example, we have a head select signal. Okay. Sorry, here it is a P select. So P select is for a particular master to all slave, it is connected. Master to slave 1, master to slave 2, master to slave 3. For all the slaves, it is shared. Okay. In AHB protocol, shared bus protocol for multiple master and multiple slaves. Here we have multiple master. We have, that means here we have only one master. Here we have up to 15 master, and we have up to 15 slaves. Okay. Here all the codes or signals are shared to all the slaves and masters. Overcome these limitations of shared bus protocol between the master and the slave. In AXI, we have individual signals. Okay, where we don't have a shared bus. And it will operate in two phases, APP protocol. One is setup phase, another one is access phase. The setup phase, access phase, what we will do, that we will discuss in detail while seeing this APP protocol. Then AHP, here we have bus request. Okay, if multiple masters are there, we need to generate this signal. Okay, that is we have arbitration, means we first request for bus and we grant. We have address phase and data phase. Okay. Here in AXI, it is happening in three phases. One is address, data, and response. Here in APP, we don't have bus data transfer. Okay, bus transfer means a high-speed data transfer happens sequentially. If you send the address once, continuously you can able to send the data, sequence of bytes of data you can able to send. Okay. So here we don't have a bus transfer, and this AHP and AXI will support for the bus transfer. Here in AXI, we can simultaneously perform write and read operation, but in AXI, in AHP, we can't do simultaneous read and write. Okay. Once you have to perform write operation, then you have to perform read operation. But in AXI, you can perform simultaneous read and write. Okay, now we are going to see about the APP protocol. So Amba 3, okay, their Amba 3 version, they released APP protocol version 1. So these are the features. Okay, we already discussed in the table. It's a low cost interface, minimum power consumption, reduced interface complexity, low bandwidth, and not a high performance. Okay, it is only used for low performance communications. Then here we don't have a pipelining concept. Here in this protocol, all signals transaction are only related to the rising edge of the clock, and then every transfer takes at least 2 cycles. Okay, minimum 2 cycles is needed. One is if you see, it is operate in two phases. One is setup and access. For setup we need 1 cycle. For access we need 1 cycle. So minimum 2 cycles is needed. It may take more than 2 also. Then APP version 1. Here when compared to these versions, APP and APP2, So in this version, they introduce these signals P ready. Okay, this is to extend the APP transfer. That means when P ready is 0, it will extend the transfer. Okay, that we will discuss with the waveform. And another signal, error signal, P slave error. Okay, to indicate the failure of the transfer. This will be indicate the failure of the transfer. These are all the signals we have in APP protocol. So please select, okay, how many slaves you have, that much P select will be available here. Okay. Then P enable, then P address. So this P indicates, this prefix P indicates that we are dealing with the APP protocol. Okay. So when we use the AHP protocol, we need to use the prefix H. Okay. Then these are the main signals. One is P select and P enable, P address, P write, then P write data. So these are all the output. Okay, let's assume APP bridge is act as a master and we have a APP slave. Okay, these are all the outputs. Okay. So this slave will receive all these output as a input, okay, and it will respond. That is, it has three output ports. These are P ready, okay, P slave error, and PR data. These are all the outputs. Okay. This is the output of slave and it is the input of the master, PR data, and system bus interface is nothing but the P ready and P slave error. Okay. So for both master and slave, you should give P reset and P clock. Okay. This is the global signals we need. So you should remember these pins. Okay. One is P select, P enable, P address, P write, PW data, PR data, then P ready and P slave error. Okay. These are the signals. These are all the inputs and these are all the output signals. Now we are going to discuss how the transfer, write and read transfer is happening. Okay. So transfer, write we are going to see. So write happening in two ways. First type is with no wait state. Okay. Another one is with wait state. Without no wait state, that means when P ready. Okay. When P ready is 1, we don't want to wait. If we want to wait, when P ready is 0, we need to wait for one more cycle, then we can do the operation. Okay, that we will discuss here in detail. Okay. So I already told, here we have two phases. One is setup phase and access phase. So in setup phase, we need to set up all the control signal and the data. Okay. Let's see here. So P address. So I am giving, just see this cycle. So here I am setting the address value. P address, then P write. P write decides whether we have to perform write or read operation. When P write is 1, it will perform write operation. When P write is 0, it will perform read operation. Here I want to perform write operation, so I make P write as 1. And P select, it is used to select the particular slave. Assume that here we have only one master and one slave. I am giving this P select for that slave to enable that slave. Then PW data, I want to perform write operation, right? So I need to send the write data. So I set write data here. Okay. So here I assign all the values except this P enable. Okay, P enable I have to assert in the next cycle. From this T2 to T3, I want to assert or I want to make P enable as 1. Okay. In the setup phase, I have to assign all the control signals and write data. In the next cycle, it is called access phase. In that phase, I have to make my P enable as 1. Okay. When I make P enable as 1, P ready. Okay. What is P ready? P ready is the response of the slave. Okay. when I make p enable as 1, if I get response from the slave, that is p ready is 1, okay, so it will perform the write operation at this passage of clock. Okay, whatever the data is available here, that will be loaded in the memory in the slave. Okay. So once it completes, I want to make my p enable 0. Okay, as soon as when you make p enable 0, automatically the slave should respond with p ready to 0, and you have to make p select as a 0. That means when you make p select as 0, that is mean that the transfer is complete. So now this is without wait. Here we are not waiting for anything, right? When p enable is 1, at the time p ready is 1, so we perfectly complete the write operation. So when we need to wait, okay, these explanations I already explained, right? The same thing. So write transfer start with the address, write data, write signal, and select signal, all changing after the rising edge of clock. All changing after the rising edge of clock. Everything I am setting here. First cycle of the transfer is called setup phase. Okay, this setup phase from T2, T1 to T2. After that, clock edge P enable is asserted. That is happening in access phase. After this clock, the next I am making P enable as 1. It is called access phase. Address data control signals are remain valid throughout the access phase. In the access phase, address, this write data, okay, then P write, everything should be remain same. P enable is deasserted at the end of the transfer. Once it is done, we have to deassert the P enable. The select signal, nothing but P select, also goes low. And I deassert it, P select should be go low. So this is for no wait state. Okay, now I'm going to explain about wait state. In access phase, when P enable is high, the transfer can be extended by driving P ready low. So first phase is same, setup phase is similar. Okay, P address, P write, P select, and P write data we are giving. The access phase, I am making P enable 1, but the slave is responding that P ready as 0. Okay, that means it is not ready. So we need to extend these signals for further clock cycles up to when P ready becomes 1. Okay, so that it is called as a wait state. So here it is 1, but it is 0. So the data and address and P write, P select, all signals will be wait. Okay, it is constant. It is stable for the further clocks, okay, until when P ready becomes 1. Okay. When P ready becomes 1, it will accept whatever the data present here, that is loaded to the memory. After that, the next cycle itself, we have to make P enable as 0. So when P enable becomes 0, P ready should be become 0, and P select should be 0. Okay. So this is about with wait state. The next is read transfer. So similar to write transfer. Okay. So here in read transfer, we want to make this P write as 0. That means it is a read operation. So here in setup phase, so this example is without wait state. So P address we have to give P write. I am making 0. So it is indicating it's a read operation. P select we have to make 1. Here we are not using this PW data. The write data is not needed. Okay, here we are going to perform read operation. So in the access phase, you have to make P enable as 1. When you make P enable as 1, at the time, slave should respond P ready as 1, and you should get the PR data in the read data in the PR data. Okay. So in the next cycle itself, we have to make P enable as 0. To make P enable as 0, P ready should be go 0 and P select, we have to make it 0. Okay. So if we are going to implement with the wait state, so P ready is not becoming 1. When P enable is 1, P ready is not 1. So we have to keep this address, then P write, P enable, okay, all these signals stable for the further clocks. Okay, when P ready is 1, that means slave is ready. So at the time I will get the read data, okay, in PR data. Then after the next cycle, I have to make P enable 0 and P ready, automatically it will go to 0 and P select is 0. If the transfer is completes, I have to make this pre-select 0. Again, if I want to continue with some other transfer, I will keep pre-select as 1, and again I will send the next address. Okay, next I want to perform a write mix. I have to make this 1. Okay, and I want to pass the write data. In this way, I can proceed this. Here, one point is here read. It is you see, I will explain. It is asynchronous with the clock. As soon as I make P enable as 1, P ready becomes 1. The data also I am getting. It is not waiting for the next clock edge. Okay. So it is asynchronous happening. Then error response. Here P slave error. Okay. This is the signal indicate error condition of APP transfer occur on both read and write transaction. Please slave error is only considered valid during the last cycle of the APP transfer when P select, P enable and P ready all are high. Okay, that means this P slave error, why it is coming, that I will explain later. So here this P slave error should be asserted or should be become 1 only when P select, P enable and P ready are 1. That means okay, here this is the setup phase. I am assigning P address, P write, P select and P write data. The access phase I make P enable as 1. So when I make this one, it is responding with 0. Okay. So it should be wait for one more cycle. So here it becoming 1. So the write operation takes place. Okay. So if P slave error, okay, why it is coming means P slave error. If I pass the address, one example why I am getting P slave error as 1 means if I pass the address out of boundary range. For example, my memory capacity is up to 256 locations are there. Okay, I am passing some 300 location. Okay, so that location is not available in the memory. So how I can tell that to the master by responding P slave error. Okay, when P slave error is 1, it will tell to the master that this address is not available in this lane. So here when it should be 1, okay, it should be 1 when these signals, these select, let's see here, if you see here in this position, P select is 1, P enable is 1 and P ready is 1. And both signals, sorry, these 3 signals should be 1. Why? P slave error is 1. Okay, once the transfer is complete, you have to make P enable 0, then P response, P slave error and P select will go to 0. Okay, mapping of P slave error. Okay. So if I use a APP to XI bridge, okay, this P slave error is mapped with R response and B response. So these are the two responses signals used in AXX protocol. So when I use a bridge, okay, in the SOC, if I use a bridge, these response signals are mapped with this slave error. In case if I use AHB protocol, AHB to APP bridge, in AHB we are using H response. Okay. So this signal is mapped with P slave error, which is used in the APP. Okay. Okay, these are the operating states. Okay. So initially it is an ideal state. Okay, I am explaining the how the APP protocol will work. Okay. So what we discussed in the waveform, the same concept is explained here. So initially it is ideal state, that is P select and P enable is 0. That means it is in ideal state. Okay. So in the next cycle, what we are doing, we are giving the control signal and we are making P select as 1. That is in the setup phase. In the setup phase, we are making P select as 1 and we are giving P write, we are giving P address. Okay. So all these control signals we are making 1 here. Okay. At the time P enable is 0. In the next cycle, in the access phase, okay, we are making P enable as 1. Okay. Then if P ready is 0, that means it is a wait transfer. Okay. Again it will be remain in the same state. All the values P select and all the control signal and data signal will be same. Okay. Until P ready become 1. Okay. So when P ready is 1, that means a transfer is complete. Okay, again P enable goes to 0. Again I am setting the next address. Okay, next whether I want to perform read write, all those signals I am giving. Again if I make P enable as 1, it will do the next operation. So once I complete all the transfer, for example I want to perform write operation for 10 bytes. Okay. So 10 times I want to perform a write operation. So I can perform write operation here 10 times. I want to make P enable 1 and then again I want to make P enable 0 and sending the next address and next data, and I am making P enable 1. Okay. So that the data will be write to the memory. So again I make it 0 and give the next address and next write data. If I make in access file, if I make it 1, again that P write data will be loaded to the P address. So if I complete the 10 transfer, I want to start the transfer. So I want to make P select as 0. P select and P enable is 0 means, so it should respond to P ready as 1. Okay. So I go to the ideal state. Okay. So here if I go means the complete transfer is finished. So you can able to design this APP protocol with the help of this FSM, that is operating states. With the help of this operating states also you can able to design, or else you can design with the normal way.